We want to find the solution of this differential equation using Laplace transform. First, we use the fact that Laplace transform of y double prime is s squared ys minus sy0 minus y prime 0, where this capital Ys is the Laplace transform of y. So applying that, the first y double prime will be this much, as said above, and then this y will be capital Y of s. On the right side, you can consult the table of Laplace transforms to say that it's s over s squared plus 5 squared. Now, plug in the initial conditions 9 and 3, so this will become 9s and this will be just 3. Collect the y of s together, so it's s squared plus 25 y of s, and then move the 9s and 3 to the other side. Make sure that your signs change. And then you have to divide by s squared plus 25. 25 is 5 squared, so it's actually same as this one. So if you divide, the first 9s plus 3 will be divided by s squared plus 5 squared, whereas the next s squared 5 plus 5 squared will be divided by s squared plus 5 squared squared. Okay, now we have this y of s, but that's not enough because we need to know what y of t is. That means we have to do the inverse Laplace transform. So you need to do the partial fraction expansion of this thing. Now, the partial fraction expansion for this is somewhat strange. I mean, this is expected, but you might see that this is not cs plus d as usual. It's not even cs plus 5d. It's something really strange. And the reason we have such a strange partial fraction decomposition is because if you look at the table of Laplace transforms with a, since in our case a is 5, if we change to 5, then this is s over s squared plus 5 squared, which is cosine 5t, and this is 5 over s squared plus 5 squared, which is sine 5t. And then when you go to the squared part, we need the s squared minus 5 squared because this over this gives you t cosine 5t, whereas the 2 times 5s over s squared plus 5 squared squared is this part. So it looks really complicated compared to what you were used to doing in, say, when we are doing partial fraction expansion for integrals. But this is the best way to do it. If you don't do it this way, then it becomes really hard later. Even after you get the A, B, C, D, if the format is different, then it's almost impossible to correctly figure out the inverse transform. Okay, so you have to do it this way. Now we're going to multiply s squared plus 5 squared squared to every term that we see, and then you can see that they cancel, and you end up with the following. We expand the left side. By the way, usually when I'm at this point, I plug in values. They say s equals to 0 or s equals to 5. Those can give us some idea of what these numbers are. But you know, when you have these s squared plus 5 squared, because nothing can make this 0. A lot of times I find that when you have s squared plus 5 squared or stuff like that, it's just actually easier just to expand everything and simplify. Okay, so that's what I'm doing. I'm expanding the left side, expanding the right side, and then I collect the s cubed. Well, there's only one s cubed, as cubed, and then there's 5bs squared and cs squared, so they can be collected together. Also for the s, 25as and 10ds is here, and then 125b minus 25c. So you set them equal, and then you let the coefficients be equal, because this equality is equation. It's an equality between functions. They are equal as functions, and for two polynomials to be equal as functions, all their coefficients must be equal. So that's what we get. We get a value immediately, and then we get some other values. Oh, sorry, this should be 6 I made a mistake there. But anyways, if you have 6, if you have this, then you can easily solve it by first plugging in the a value 9 here, and you subtract it over to the other side, and you get d equals 1/10. And then for this one, you can divide everything by 25, which gives you 5b minus c equals to 3. And since 5b plus c is 3 and 5b minus c is 3, if you add these two values together, you get 10b equals to 6, which means b is 3/5, and then you can also see that c is 0. So you get these values and you plug it back into above, and this is what you get. Now, I didn't want to tell you this in the previous slides because it's going to ruin the fun, but if you actually see what's going on, you see that actually you can just, without ever having to do the partial fraction decomposition, this is already decomposed in the way that, in the format that you want. See, 9s, same thing, right? 3 is 5 times 3/5 if you cancel the 5s, right? And then s is just 10 times 1/10 times s. So you could have just, if you knew what you were looking for, then you could see that this is already in the form of partial fraction expansion. And then once you have it in this form, then you can just read off to figure out the yt. The inverse transform of s over s squared plus 5 squared is cosine 5t. 5 over s squared plus 5 squared is sine 5t. And then 10s over s squared plus 5 squared is t times sine 5t. And then you have this 1/10 coming from this 1/10. Okay, 3/5 goes here. So that's the answer.